I guess we'll go ahead and get going with our afternoon program. How's everybody doing? How many jet-lagged people do we have who are starting to die? A couple. Yeah. So I'll try to keep it lively to keep you awake. A couple people have asked me, the printed out paper schedule that you got in your folder yesterday or this morning, there's some errors in it. And it includes things like the 2 Fridays for the lectures are identical. So that's not happening. We're not doing the same thing repeated all over again. So when in doubt, if you guys go to the CITER webpage and look at the agenda on the wiki, that is correct. So the default for you should be the wiki and not the printout. But if you have questions about the schedule or when there'll be time to do certain things, you should definitely feel free to ask myself or Peter or Doug. And well, there's some flexibility built into the schedule, not a ton, but there's some. So we can handle. I have a couple people ask me things already about can we fit them in. So. Any other sort of like logistics or questions before I start talking about petrology and geochemistry? Yeah. Are you raising? You're not raising your hand. Okay. Okay. We can all do like a group stretch together before we start. All right. So I'm Christy Till, and I am one of the organizers, and I'm going to give a very broad view of what we think about as a petrologist or a geochemist, or even just as a geologist who's looking at a subduction zone. So how we look at those things and what that view might look like if you could put on your petrology glasses and see the world through them. What would you be seeing? And to start us off, this is a line drawing that I did as the advertisement for my PhD defense a number of years ago. And I think it actually kind of encapsulates some of those things. I was thinking a lot about subduction zones and how magmas were generated in subduction zones. And you can see like the scale of certain things is like very disproportionate to reality, which reflected the things that I was thinking about a lot, right? Those birds, for example, are definitely not to scale compared to the mantle wedge, but yeah. So I'm gonna go really broad here. I really want you guys to interrupt me constantly, ask me tons of questions. I'm going very, very basic. So if you have a question about something that's, trying to go more advanced, that's great. Or if you have something that's like really basic, like this week, and especially these first couple of days, these are the times to like ask that really, really simple question. And there's no shame, okay? So please interrupt me. And we have the microphones, but another strategy is to just really shout, so. Okay. So I thought I'd just say a few words about who I am, since many of the students, for example, probably have no idea who I am. I am a petrologist, and mostly I'm an igneous petrologist, although I look at metamorphic rocks, or sometimes you can ask the question, what is the mantle? And I look at the mantle, so if it's igneous or metamorphic. The main instruments that I use are experimental apparatus, which you can see here in our lab at Arizona State University. And so these are a range of piston cylinder devices that cover from 0 to 4 GPa and up to about 2,000 degrees Celsius. So we're looking at the lower crust and uppermost mantle part of planets. Here's my wonderful research group. And we have, a very broad interest in how magmas form. I would say the sort of biggest question, or the broadest question we ask, is sort of how do magmas form in the context of planetary bodies? Over what time scales do they form? And what role do they play in sort of the formation and evolution of planets? But some more specific questions is we think quite a bit about how the recycling of oceanic plates produces volcanic arcs, so the magmatic sort of cycle of a subduction zone. We think about what are the specific events in a magmatic system leading up to an eruption, and trying to back out that life story of a magma body before it erupts, and specifically the time scales associated with each of those events prior to eruption. I'm working on exoplanet mantles, trying to understand melting behavior and crust on exoplanets, and also thinking a lot about how subduction zones and the roles of the solid Earth might have contributed to the rise of oxygen in the Earth's atmosphere, what we call the Great Oxygenation Event about 2.3 billion years ago. So a very broad range of interests in magmas. So please, I'd love to talk to each and every one of you about anything of our interest that might overlap during the next several weeks. So I look forward to having conversations about all of those things and many more. So I'm going to talk about a couple of things here you can see in the outline. I'm going to first just really basically walk us through the key components and processes in a subduction zone if I'm wearing those petrology colored glasses or a geochemistry colored glasses. What are the things that pop out to me? What do I look at? I'm going to talk about some of the key tools that we use as geochemists and petrologists, and then sort of think a little bit about what are the big picture questions that these communities are thinking about today. And I'll end with sort of a roadmap for all of the geochemical and petrologic and geological contributions to the lectures over the next couple weeks and show you what the roadmap is for those and how they're going to fit into this big picture that I've just laid out for you. So let's just get started. So here's another cartoon that I'll be using throughout, and we look at a subduction zone in a cross section mostly, right? We're not quite advanced enough to look at it in 3D on most days, and then the reality is we think about it in a cross section, but that is a very idealized cross section. As we were talking about this morning, the slab is not like a perfectly linear feature with like sharp boundaries or anything like that. But we think about it like that because that's the models that we've developed. And so we always have to ask ourselves how much of what we're thinking about or interpreting is based on these models we've created for ourselves, or these cartoons really, or how much of it is there a different way that I could be thinking about this. But this is how, in my head, when someone talks about a subduction zone, that's the context I'm usually putting it in. And the reality is that most people who walk around the surface have never seen this or heard about this or think about this. They think about this, right? And maybe they don't even include this part, right? They might be vaguely aware that there's a chain of volcanoes up and down the Pacific Northwest if they're in America, or in the Ring of Fire, and that those are there, and that they're maybe aligned in some distribution. And it's also important to think about that these are, when a geochemist is interested in thinking about the processes that happen in a subduction zone, these are the main places that we go, right? So any view that we have of a subduction zone is biased to what these tell us. Because that's where we've been able to gather the most information so far. It's not that there's other sources of information, it's not that we don't look at them, but just historically, that's where the majority of our emphasis has been so far, and so our view is biased towards those. So we kind of divide the subduction zone up into sort of quadrants or parts. And we tend to, even within the communities of petrology and geochemistry, we don't all work on the same parts, right? So one part that people tend to divide out is sort of the subducting slab itself, and the materials that are in it and the processes associated with the subducted slab. There's the mantle wedge. Here I'm including the lithosphere part of the mantle wedge, but sometimes that's not. The asthenosphere part of the wedge, and that's like a community of people, community of tools who focus on that. There's the crustal part, in which I'm including the arc in that, and there's a community who focuses on that. And it's not that any group of scientists don't cross those boundaries, but we do sort of self-organize in some broad regard into those. And so not only do we need to be interdisciplinary in our geophysicists talking to geochemists, but it's always really good to make sure that the views that we're thinking about in the arc are linked to what's happening deeper below. Like a lot of cartoons, right? They go like, a cartoon of a volcano ends in the upper crust, right? They don't go deeper than that, right? And so how do we sort of think about these as a whole system? So, and then there's volatiles and magmas which transit through all of these different parts. And so they are the parts that sort of link all of these and force that sort of cross pollination of discussion as they migrate through the whole system. But as geochemists, these are sort of maybe the ways that we most commonly, or at least I can't speak for all geochemists and petrologists, so this is certainly biased towards my view, but that I tend to sort of divide things in my head or see the world of science divided into. So what I'd like to do now, I'm just going to sort of step through a subduction zone and say, as a geochemist or petrologist, at each step along the way, what are the key things that we're thinking about? What are the key processes? So this is going to be really basic, but hopefully useful, and sort of just going back to the knowledge so that we can all be on sort of the same playing field as we talk about this stuff. So the very first thing that's important for a subduction zone is the formation of the subducting plate itself, right? So that actually starts over here at the mid-ocean ridge. And as Peter discussed this morning, there's all sorts of important processes that sort of set up what's going to happen in the subduction zone in the mid-ocean ridge environment. There's melting that's happening here to source the magmas that then go on and form the oceanic crust part. There's slow cooling that facilitates the formation of the mantle lithosphere part of that oceanic lithosphere. There's, I don't have it written up here, but there's the deposition of sediments away from the the ridge axis. And there's hydrothermal circulation, which is a really important mechanism to introduce fluids close to the mid-ocean ridge. But then there's also very important outer rise faulting that we talked about this morning that introduces fluids not only into the oceanic crust, but into the oceanic lithosphere portion of the slab. And so it is this setup that is so elementary to understanding the flux into a subduction zone environment. You really can't understand what, the sort of net cycles without understanding what's going in.
Christy?
Yeah.
Do we have a sense of the relative importance of the hydrothermal circulation versus the bending fractures in terms of the water that they produce? Are they comparable? Or are they different?
That's a great question. I don't know, Magali or anybody else want to chime in? I think, yeah.
Are you talking about hydrothermal circulation near the mid-ocean ridge?
But it ultimately adds water to the plate.
That's an important.
You can have hydrothermal circulation in the cold bending area too.
Right. So, so there's hydrothermal circulation close to the ridge axis, which has certain chemistry associated with it, certain temperatures associated with it, and then there's additional hydrothermal circulation as you sort of move to cooler parts. There's also the outer rise faulting. I remember having a conversation like early on, maybe in my master's degree, where someone was like, that was not discussed at the time as an important mechanism. And so, the evolution of that as an important mechanism or maybe a main mechanism to introduce water into the subducting slab has really, at least in my knowledge, has really grown in appreciation since, the late 2000s. And so, to be able to say the ratio of how much one versus the other introduced, I think is an open question, at least to my knowledge. The one thing that's clear, though, is that because of the amount of oceanic lithosphere close to the axis, the amount of water that ends up in the oceanic lithosphere is a really important component, and probably those outer rise faults are a very important part of introducing it into that colder, more developed lithosphere, depending on where the axis of the ridge is relative to the trench, obviously, but yeah.
So in my naive mind, hydrothermal circulation means hot stuff is going up, and the outer rise faulting means cold stuff is going down. Is that something that you could distinguish geochemically?
I'm sure there's ways we could think about how to distinguish it, but there's
circulation starts off as cold stuff going down.
Right, exactly. I was going to say that the characterization of the stuff near the axis is actually starts out cold, right, and then it gets heated up. So it's a little bit more complicated than thinking of them as being sort of two separate thermal regimes. Yeah. Do we have, Samir has one and then Magali has the other. Okay, so let's, We can have maybe volunteer runners who can like run around. If you want, like if you're afraid you might fall asleep after lunch, that would be a good activity for you. Yeah, all right. So this is the setup, right? And then I just thought I'd touch briefly on, well, what are the materials themselves, right? So that slab that we've created, essentially, we can think of it as the 3 basic parts. The sedimentary layer that caps the top. And this is, often examined by looking at drill cores of various types. And there's both biogenic and terrigenous or continental derived sediments that contribute to the sediments that sit. So they're not uniform in composition, they're quite variable in composition. They vary in terms of where they are globally, in terms of the amount of those 2 components. They vary in their thickness depending on how old the oceanic crust is, and so they are a variable and important component. We have the oceanic crust part, and in the simplest sense, this might be the part we're most familiar with. We think of it as a basalt, a mid-ocean ridge basalt, with a fairly uniform composition, although that's not in fact true. There is variation in the composition. And then the maybe most dominant portion of that subducting slab in most cases is that lithospheric mantle. So that is volumetrically quite significant, and it in fact, is an incredibly important reservoir for water and other elements that are volatile, that are carried in volatiles. And the mantle itself is broadly, we call it peridotite. That means that it's made up of olivine, which is this nice sort of candy apple green here. Pyroxene, which in this one is a darker green, that's kind of hard to see. And then variable amounts of minerals that have aluminum in them. So in some cases that's feldspar, in other cases that's spinel, in some cases that's garnet when you're a little bit deeper. And that the ratios of the aluminous phase vary, and therefore the relative proportions of olivine and pyroxene can be more or less dominant compared to these. When we start talking about melting the mantle, these aluminum-rich phases are the things that melt out first, and these are the more residual things, the things that are less likely to melt. And then when we start adding that water to the oceanic crust and lithosphere, we are then developing additional minerals in the subducting plate that are hydrous in nature. And the ones that you hear most commonly discussed and are the dominant ones for these compositions are amphibole, which has about 2 weight% water, serpentine, which we've heard a lot about already today, that has 12 weight% water, and my personal favorite, chlorite, which has 12 weight% water as well. And so these, we often talk about one or the other of these minerals, and I think it's important to think about their coexistence or the relative proportions of these, because they have different implications. They break down at different temperatures. They are associated with different mineral chemistry, so on and so forth. So these are what are being introduced as we subduct the slab. So then we have the slab, and it starts going down into the subduction zone. We can think about why that happens, but as a geochemist or as a petrologist, that's not normally something I spend most of my time thinking about. So, but there's very important implications from petrology and geochemistry about why. So there's the metamorphic reactions that change the minerals present as the pressure increases dominantly, and there's some increase in temperature, and that therefore also changes the material properties of the slab. And the one that most people are probably familiar with is this transformation of the oceanic crust into eclogite as it gets to higher pressures and temperatures, such that there's a dramatic change in its density. The minerals that are in eclogite have a much higher average density compared to those that are in the oceanic crust to begin with. So there's this series of metamorphic reactions that are happening, and those are associated with dehydration reactions. So we start to see the breakdown of all of these hydrous minerals that we've set up through that introduction of water to the plate. And there's important relationships between these phase transformations and earthquakes. We've seen quite a bit already in discussion so far. And I'm not going into those, but just to sort of remind us that when we're thinking about metamorphism, these topics are all intimately related to one another. And there's some very nice summary papers. This one's already been referenced, or these two authors have already been referenced earlier today. A nice thing about all these lectures being available is for students, if you want kind of a review paper on a subject, I've tried to cite them here so you can go back and look it up and read it. I remember when I was doing this during my degree, that was a great way for me to sort of develop my knowledge base, was hearing someone mention an important paper and then scribbling it in my notes and going and reading it. So, or I'm happy to direct people to some of those key review papers on a subject. So this is a review paper that goes over, at the time of its publication, sort of what we know about the phase transformations in the subducting slab itself. And those are drawn here. So we have different minerals here. So here, the AMP here, in this case, this is amphibole. And so amphibole was a mineral that we heard discussed a lot, say prior to maybe the 1980s, 1990s, as an important contributor of water to subduction zone processes. But what we have subsequently learned is that its pressure and temperature stability is such that it's mostly devolatilizing in the shallow portion of the slab. So in the sort of below the forearc. So it might be very important, for example, in something like these serpentine volcanoes or serpentine seamounts we were talking about this morning, but it's going to be less important when we get down to the depths where melts are generated in subduction zones. There's other minerals in these green dashed lines here, like chlorite, which was that one I mentioned before, antigerite, the 10 angstrom phase, which is just another form of this same hydrous minerals. And then there's some amount of water that makes it much deeper. And on the purple here are the phase transformations that are associated more with the oceanic crust portion of the slab. And so you can see there's key ones. And there's some variability in these depending on composition and new references since then, but this is a nice overall picture. Any questions? Yes?
Can you discuss which phases might effectively transport water to pressures beyond 10 GPa?
Well, yes. There's a great body of research that's continuing on this. We don't have like simple, clear answers, but rather than me try to review it all right now, I'll just simply say that it looks like there's one of the key questions might be how much is the relative proportion of water that makes it past sort of this what we'll call subduction filter and into past that portion of melting and devolatilization in the shallow part that can make it into the deep mantle. And our estimates of those ratios have gotten better as we understand more about those high pressure mineral phases. Obviously the thickness of the slab and the hydration of the slab are going to control that ratio. But one of the main carriers is probably some of these phases that here is called the A phase. And these are all essentially, if you think of, if you have any familiarity with sort of the talc or brucite crystal structures, which are these, sheets, these sheet silicates. These are all, like chlorite, for example, the 10 angstrom phase, are just different arrangements of those as you go to higher pressures. And so their chemistry, we might be able to fit other things into them, but it's dominated by those same elements, magnesium, in some cases iron, and silicon, but they're not sort of some weird mineral that we've never heard of. They're just a rearrangement of those same atoms that might be found in a chlorite, for example. Does that make sense?
In this picture, I get always curious about these potassic mineral phases.
Yeah.
And they go so deep in their light ion lithophyll elements. Any comments on that?
Sorry, what was the last part of your question again? Like,
why the potassic mineral phase goes so
deep.
Yeah, and they have like a potassic amphibole or phyllosilicates.
well, yeah, there are versions of this where these aren't quite so deep too. It depends on the persuasion of which set of experiments you like.
It's a cartoon.
It is also a cartoon, right? But why those particular minerals are stable to a higher pressure, I don't have a good answer for. I don't know. Sarah, do you have any? Okay. All right. Well, like, we can put a pin in it, right? I think one of the really nice things to do while we're all here would be someone scribble down in your notebook, right? Like that question, and maybe we can figure out an answer to it. You know, either as part of a research group, or maybe just we can look up an answer, right? And then it would be very satisfying to all of us. So, yeah. Any other questions on the metamorphism sort of general part? So we're metamorphosing the slab, we're changing the mineral phases in it, we're devolatilizing it, which has important relationships with earthquakes. And then the main thing that starts to happen is part of that devolatilization, though, there's other things that might get fluxed from the slab along with just aqueous fluids. So we have the possibility to have all sorts of things separate from for the main part of the slab, for sort of lack of a technical definition, and mobilize into the sort of asthenospheric mantle portion of the subduction zone. So aqueous fluids is the ones we think about most commonly, but we have evidence that you can have perhaps sediments that are less dense than the surrounding material, and such that we actually have diapirs of sediment make their way. There's some studies that show that into the mantle wedge, where then eventually they do melt because they encounter high enough temperatures to do so, but they are not inherently already melted perhaps when they separate from the slab. We also have potentially melts of the sediments themselves. So even if they don't make it off in a diapier, it's possible that they melt sort of at the conditions closer to the slab surface. We can have melts of oceanic crust itself. And then we could also have combinations of these, and I put here supercritical fluid. How many people know what a supercritical fluid is? All right, a few hands. So a supercritical fluid, in this case, for example, a good way to think about it would be at high pressures, if you have a aqueous fluid that has a lot of solute dissolved in it, so a lot of little bits of minerals that have been then dissolved into the fluid because they have high solubilities at those conditions, or if you have a melt that has a lot of aqueous fluid dissolved in it, at some point and at some pressure and temperature, we can't tell the difference between those two things anymore. We can't tell the difference between an aqueous fluid with a lot of solute and a melt with a lot of water. And so those things are supercritical fluids. Essentially, it's a phase that's a combination of a silicate and aqueous material and so it's one, we have lots of questions about exactly where those points happen, what pressures and temperatures are required in a subduction zone environment to have, it's not an aqueous fluid and a melt, but to have the supercritical fluid. But we also have a lot of questions about, well, what is the behavior of that material itself, and how does it behave compared to a melt or a fluid that we're more used to thinking about?
So what is the depth of that? Is that a miscibility boundary or something? So there's experiments. Because I keep hearing different numbers.
Right. So there's a problem of small statistics. There's only a couple of papers that have, so the way we try to do it experimentally to determine where that happens is very challenging. You have to do it in, for example, a multi-anvil press at a beamline where you can actually have visibility of the experiment while it's at high pressure and temperature. And you're looking for essentially the formation, that immiscibility, where you start to see a separation of the two of them, and actually being able to see like a boundary of, say, a bubble, for example, is a very challenging thing to do. So if you don't see the bubble, does that mean that there's not two separate phases? So there's some experiments, there's like 2 or 3 papers now, and they're in conflict with one another. So where we think that happens, it's possible that it happens in the pressures and temperatures that are very relevant for all of the processes that we think about in the mantle wedge, in one case, and the other one, it's much deeper. so like 6 or 7 GPa. So whether or not that this is an important component of subduction zone processes is still sort of an outstanding question. Yeah?
Is there a good idea of how much of the sediment actually makes it to melting depths versus gets off somewhere?
I don't know off the top of my head. Does anybody feel like they can speak to that?
I think it varies from margin to margin.
Right.
Okay. So my question was, is there a good idea of how much of the sediment actually makes it to melting depths?
Right. Yeah, it does. Sarah says it probably varies between different subduction margins, and depending on how much sediment there is, how thick that package is, what the thermal conditions are in a particular subduction zone. But I don't have sort of like sense of what those ratios are. So, so there's all of these things that people have found, for lack of a better term, they have found evidence. So there's papers published that says all of these things come off of the slab. Now, how much comes off the slab in a given subduction zone with a given thermal structure, is a good question, and it might vary quite a bit. One way to think about it is in the context of diagrams like this. So we have temperature increasing on the x-axis, pressure increasing on the y-axis, and depth over here increasing. And so here in red are the slab surface PT paths predicted by one set of geodynamic models that are widely cited, those of Syracuse et al., created by some of the people in this room. And this is, so here, for example, would be a very hot subduction zone, cool subduction zone. And so here we're looking at the transition from where you start to have more of that viscous coupling, which is sort of causing this bend here. So these only reach the coolest temperatures, and then warmer subduction zones, so this might be what? Japan or Marianas, right? Tonga, right. And then here we have Cascadia, for example, which is a warm end member in terms of its temperature on the slab, predicted temperature on the slab surface. So here I'm drawing a bunch of phase boundaries that are relevant for these questions. So here is the temperature in purple that the oceanic crust melts at, okay, when there's water around, which there's a really good chance that there's water around in the subduction zone. So the oceanic crust here, so in very warm subduction zones, you can cross this temperature of melting, within the range. So this gray box is like the thermal conditions sort of in the mantle wedge right above the slab for global arcs today. So in some subduction zones, it's totally possible, these warm ones, where we might melt the oceanic crust. And then other ones where it's very cold, we're below the temperature of the melting curve, and so it's very unlikely that we would melt it. The sediment here, sediment solidus, again in the presence of water, and this is one composition of sediment. This isn't all sediment, but it's sort of a global average of sediment. Its melting curve is right here in the yellow. And so you can see that sediment could very easily melt again in these warm subduction zones and in some of the intermediate ones, but unlikely to melt in the cool ones. So these thermal models obviously have their own pros and cons, but these are sort of some of the ways that we think about whether or not we're getting certain kinds of fluxes off of the slab in a certain kind of environment. This is the water-saturated solidus for the mantle, so showing us that where we're going to start getting mantle wedge melting immediately adjacent, because remember this is the slab surface temperature, so immediately adjacent to the slab. Any questions about that?
So just to clarify that, that's the mantle wedge temperature directly adjacent to the slab, so in all those you would still expect melting? You
would still expect melting, but you just expect it a little bit above.
In the core of the wedge?
Yeah,
okay.
Or higher up, yeah. Where there's only some subduction zones where you can basically, you have to have enough water around for this process to happen, but in some of the warmer subduction zones, you have enough water around probably, and it's hot enough to do it essentially adjacent to the slab. Yeah.
Could you clarify, it seems so counterintuitive to me, why oceanic crust would melt at a lower temperature than sediment? at low pressure?
Yeah, I mean, this is, so this is in the presence of water, and essentially what we call the cryoscopic freezing point depression. The effect that water has on the melting temperature is variable depending on the material. And so basically what you're seeing in some ways, so so this is mafic, right? And bulk composition, and this is much more silicic, and you're saying intuitively to me, silicic things have a lower melting temperature in general. That's accurate. And also one thing to sort of verify your maybe intuition is that when you get up to higher pressures, you'll notice that the oceanic crust solidus is actually, in fact, at higher temperatures than the sediment solidus. It just turns out that at these lower pressures, that the effect of water is greater on the oceanic crust than it is on the sediments.
So just following up on this, so there's like infinite water, is water saturated? And
Right.
What happens to, like, sort of my picture is that these very first melts that come off carry a lot of the water with it, and then, you don't actually have an opportunity to melt a lot of the crust. Is that the right way to think about it?
So these melting curves are all assuming that they're water saturated. So that means that there's a water phase around. There's plenty of water in addition to the material itself. And so whether or not that's true is a valid question, right? So it's certainly true that the first melts of everything, the sediments, the oceanic crust, the mantle, will have a much larger water content, and therefore, but whether or not they care, like whether or not they take it all and take it all away, or if there's enough flux continuing to come from whatever source that's providing that water, is the question then about whether or not that process will continue. We did some calculations in terms of the water content from subducted slabs using those estimates that from the paper from Peters that we saw this morning, about how that water content varies as a function of slab thermal properties. And we found that I won't sort of go through the nitty gritty, but the short story is in cold subduction zones, you have enough water to a deep enough that flux is great enough that you will be able to perpetuate a lot of like the water saturated mantle melting, even after you have like first increments. Because we can calculate how much water would reside in the hydrous minerals, right? And then think about, you have to kind of have some volume estimates of melt and things like that. But in warmer subductions, you might run into a place where you don't have enough to. Does that answer your question? Enough. Okay. Yeah. Yes.
I'm not quite sure. I understand the shape of the temperature curve on the slab on the surface.
Yeah.
That it rises, the pressure rises quickly with respect to temperature, and then the pressure stays nearly constant for quite a stretch of temperature, and then swing upwards.
Yes.
Why it looks like this?
Jeff, Peter.
You're
but I'm wearing my petrologist. I'm wearing my petrologist glasses.
It's because when the slab surface basically emerges from beneath the overriding plate, you suddenly have that slab surface in contact with the warmer material from the mantle wedge. So at that corner, that point where the slab just starts to come into the mantle wedge, you heat up very rapidly over a short distance in depth. And then it continues. Then you've actually creating a thermal boundary layer on top of that slab, and so it's not heating up as much, but you are still heating up as you go down against the mantle.
Kind of.
No, the temperature increases.
Goes way up at a constant pressure.
Yes, that's where the slab emerges from beneath the overriding plate and comes in contact with the hot material from the mantle wedge.
I'm going to skip ahead so you can have a picture.
Is it?
So, right. So there's sort of a function of temperature at the slab surface. You can see here and how that changes here. Right. That's what we're talking about. where you start having yeah. Okay, we'll go back. We can keep talking about it though. These are important questions. All right, so we have all these things that may or may not come off the slab. I put them here, in order of what require increasing temperatures. And so you can kind of think about, well, what's the probability of each one of these happening, right? And that there maybe is a lower probability of the melts in the oceanic crust in any given setting and a higher probability of aqueous fluids. The supercritical fluid is kind of an open question, I think. Probably important, but to what extent it's important, we don't know yet. So then we have all these things coming off the slab, and then we engage in some sort of, we have this asthenospheric mantle that's undergoing corner flow, and we trigger some sort of melting, right? And so this is sort of like where the going gets good if you're a petrologist or a geochemist, right? This is where stuff really gets interesting. And at least in my biased view as an igneous petrologist. And so the question is, so what's happening here? Well, let's go back to basics for a second. So when I say melting, what do I mean? I mean that we're starting out with the mantle wedge in this case, which is my cartoon here on the left. And if we think about this in pressure, temperature space, on this side we have a solid, and we have to cross the solidus curve, which is the temperature at which we get the first melt at a function of pressure. We have to cross the solidus curve over here, so now we're in a two-phase field. Before we just have solid in this case, now we have solid plus melt. It might be multi-phase, though we might have different minerals. And then now we're adding into it a silicate melt. And so what starts to happen is we start to have a little bit of melt, and that melt essentially forms at and coats grain boundaries as the very first thing it does. And so then at some point we get enough melt, which is dependent on things like grain size and dihedral angle and deformation, so the strain that's accumulated, about how much of that melt that you need to have to start to form an interconnected network that then can flow away from the point that it's generated. Yes?
So my impression is that experimental data suggests that you form an interconnected network almost right away.
Right.
And that's basically what's indicated, like 1% melt, something like that.
Right.
And that's also consistent with like U-series disequilibria and those kind of data. Is that
There's, I think that we've moved to a point where we need less and less melt to form an interconnected network. What that boundary is depends on other variables. Am I right in saying that? And so where exactly that cutoff is, I think there is some variation, but yes, it's certainly at very low degrees of melting now, we think. Yeah, but.
I just, to clarify that, in addition to melt being interconnected, just because melt is interconnected doesn't mean permeability is high.
Right, exactly, yes. Yes. So we're forming a melt, but what that means depends on lots of things about whether or not it can form enough to move away and have an interconnected network that can flow away. But when we say melting, we just mean crossing this solidus. And in a subduction zone, there's actually multiple types of melting that happen, so multiple reasons that we get melting. So we'll start with the simple one. Remember back to your petrology class, or maybe you got this in Intro to Geology. So in a mid-ocean ridge setting, and in the back arc of a subduction zone, we're actually generating melts the same way. And that's by adiabatic decompression melting. So this is dry melting, and it's mainly triggered by crossing the solidus because of decompression of the mantle. So the simple act of having the mantle flow upward causes it to melt. So here we have our adiabat, so the sort of temperature curve that's appropriate for a convecting portion of the mantle. And here we have our anhydrous mantle solidus in this example. And so you can see that because of the slope of the anhydrous solidus, right, which is shallower than the slope of the adiabat, if I have mantle rise, it'll cross, at some point it'll encounter the solidus, at which point the solidus will be at a lower temperature than the adiabat, which would be if the temperature of the mantle would just kept rising. And so it is therefore energetically favorable for the mantle to melt rather than to continue rising and not melt. And that difference in temperature, or that difference in energy between the adiabatic curve and the solidus, is called the latent heat of fusion, and that's the energy that goes into melting and controls the total temperature difference between these two. Will control the amount of melting, as well as the total amount of decompression over time. So this is dry decompression melting, adiabatic decompression melting, and that's what happens to form the oceanic crust that goes into the subduction zone, and that also is what's happening when we have upwelling mantle in corner flow in a subduction zone. And then at the sort of exciting, complicated part of the subduction zone, we believe that what we call flux melting is a dominant process that's important. So here we can have the same setup that we have here. We have our adiabatic gradient, and we have our dry solidus. But now with the introduction of this flux from the slab, predominantly, let's assume water for now, we lower the temperature of the solidus such that mantle that might have not, that was at the adiabat, right, now is already above its solidus temperature, and therefore will melt. And it melts and therefore rises, and it maintains below the melting temperature. Okay, so this is flux melting or wet melting that we believe is initiated in these conditions where we're having flux from the slab meet the mantle in subduction zones. Any questions? Okay. Yeah.
So I'm a little confused. Why are the purple arrows going on the solidus?
Well, yes, this is a simplified example. As melting continues, then, right, we would continue along the solidus for some period of time, and then we would rise off of the solidus when we are perhaps entering into channelized flow and we're moving that material away. But there is a. You thought.
Some other slope that depends on the latent heat of melting.
Right. So there's yes, you're taking it a couple steps ahead, but that's totally fine. Yes. So if we continue, like when we continue melting, there's the initiation of melting and the latent heat of fusion that goes into melting could be thought of as the temperature difference between the solidus and the adiabat. If we continue melting, yes, then we will have rise along something that's sort of like parallel to this slope. Is that, yeah. My point here was to suggest, with this arrow, was to suggest that as long as there's lots of water around, we will not have a problem with the continuation of melting.
So to what extent is the back arc melting really dry? Because it seems like, at least in back arc spreading centers, a lot of times there's a lot of water there.
It's all relative, right? So here, this example that I gave for flux melting, in this scenario, you can see the amount that the solidus is depressed is a function of water content. So here I've depressed it sort of the maximum amount that I can lower the temperature because I'm doing this at water saturated conditions. If I have just some water around, so not enough that I saturate the nominally anhydrous mineral, so not enough. So if you have an olivine, right, and you can put some water into your olivine in the crystal defects and in all of the little places in the crystal structure. And if that olivine is not full of all the water it can possibly hold, then we call it water undersaturated. And if we're water undersaturated, and when we fill it up, then we get aqueous fluid and we're water saturated. If we're at water undersaturated conditions, then our solidus is somewhere between the dry solidus and what I've labeled the wet solidus here. And so it's somewhere in the middle here. And so then the questions continue to be, if we, I have an entire lecture on mantle melting in subduction zones where I can go into great gory detail about it, but the sort of simplified version is depends on how much water there is, but we can still get sort of dry melting if we just lower the solidus a little bit. This decompression melting still works if we just lower it a little bit. If we add too much, then we change the kind of melting that we're doing. And so how do we know all of this? We know all of this from many years of work, but the sort of way that we know what the temperature is and the melting mechanism itself is from experiments. So doing conditions where we take an experiment to a certain set of conditions, a pressure and temperature, and we see if it melts or not. And so here we have the anhydrous mantle solidus from a compilation of experiments by Hirschman et al. And you can see all these experiments that define this curve here. And then here I'm biased. I'm plotting my own water-saturated mantle solidus, but there's other ones, and experiments that constrain that. And so you can see, that there's quite a big difference between the temperatures that would be required to melt the mantle below a subduction or below an arc are 1400 to 1600 degrees if there's no water around, whereas if there's water around, you only need somewhere at about 800 to 900 degrees Celsius to melt the mantle. Yeah?
I'm just wondering why there's a curvature going back at
This way.
4 to 6 GPa.
Right. So exactly what the slope of this is undetermined because we don't have a good set of experiments up here. But you can think about it as, I'll say these words and I'm not going to explain them right now, so apologies ahead of time. The Clausius-Clapeyron equation, right? And so basically what we're looking at is the balance between how volume changes as we change pressure, right? That's one of the terms in that equation. And so it has to do with the relative change in volume of the solid minerals versus the melt. And then on the other side of that equation is the temperature and the entropy change, right? And so why we believe it might turn over has to do with the relative change in volumes of the melt versus the solid. Okay? Yeah.
So I guess I'm a little confused by these figures. So in case of both the solidus that you show here, aren't there just as many filled dots on both sides of the line?
Right, exactly.
So there's something else that...
So the short answer to that is that a filled dot versus not a filled dot is a very simplified way of trying to condense these complicated experiments down and show them in a figure. The reality is whether or not there's melt present in an experiment takes quite a lot of energy, and there's people, you bicker over what evidence there is if there's melt present or not present. And so there's a whole level of interpretation that goes into quality and interpretation of those dots, other than just whether they're filled or it's not like it's really simple and super binary to look at. But the fact that we have a difference over here, that there's some that are quite over further at different temperatures, this is just a fit through the data, but that you can sort of decide whether or not you agree with it based on where those go.
I guess what I was asking is there a model that's built into the lines in addition to the data that's shown by the dots?
Yes. That's the short answer.
I remember for a long time there was some kind of big argument about the water-saturated solidus. Yes. Is this still going on? And maybe would you care to
comment on it?
Give us your opinion.
Right. Well, I planned to save that for my entire lecture on mantle melting next week, but the short version is yes, there's still disagreement over it, but the actual disagreement of a couple hundred degrees doesn't change this model that much. So there are some implications of one versus the other, but they're not catastrophic. Yeah. So yeah, stay tuned. I mean, I could go into it now, but I'm just sort of in the interest of covering the material for today. Is an introductory level. So here is sort of then a more developed cartoon, which is, because that's still what it is, of a cross section, again, still in 2D, of thinking about melting. So we now have our subducting plate here, and I have outlined the hydrous mineral stabilities. Here using, this is one thermal model of a subduction zone. That's a sort of average one, but there's different ones, and where these boundaries would vary depending on which thermal model you're using. And so the darkest green is serpentine stability, and then the lighter green is chlorite stability. And then I kind of overlaid amphibole stability in this black dashed line here. So you have and this is your altered oceanic crust, and then these are the phase boundaries within your mantle lithosphere portion of the slab. So you can see immediately that you have both serpentine and chlorite being important players of however much water makes it into the mantle lithosphere from that hydrothermal alteration and those outer rise faults. They are important players in then the dewatering of the slab all the way down to basically the maximum conditions at which we see melting in subduction zones. They also are important players in this nose of the wedge here, and you can see both chlorite and serpentine would be stable at these conditions. So when you have shallower phases like amphibole breaking down and releasing water, or things in the oceanic crust breaking down and releasing water, they're contributing to actually probably forming hydrous minerals in the shallow part of the wedge. But also it's important to note that there's the possibility, depending on the thermal model, of actually having little bits of hydrous minerals stable above the slab too. And we saw lots of nice examples from seismic studies this morning that provide evidence for some of these observations. There's also geologic observations that we work on to try to figure out, to provide on-the-ground evidence for these kinds of mineral stability. My student Megan Guild has a poster this week, and some of her work is trying to map out the stability of hydrous minerals from some paleo-subduction zones based on natural samples. Yes?
Thank you. So actually, by looking at this figure, and reminds me what Peter showed earlier this morning, is that the cold corner, the cold nose, and actually what you are showing here is actually that's extending to about 50 kilometers. And what's the so-called decoupling tape depth is about 60. It's about 80 kilometers. Is there anything related with each other, or is there any comments on that?
Yeah. Well, where this sort of wall here is, or dehydration wall is, or is also going to vary, right? Depending on this is a 2D cross section, right? Maybe it vary in a 3D cross section, or also will vary globally with the changes in dip and the changes of age of the subducting slab. So exactly where that happens is going to vary. This is just based on the mineral stability, where the minerals are stable at what pressure and temperature conditions. You might think about that there's reaction rates to all these things, right? So how long does it take for some mantle to move from point A to point B so it changes its temperature, right? So as it is being advected downward. And then how long does it take for those minerals to break down and release their water, and such that you have absolutely no more hydrous minerals. Those are all, you have to think about the relative reaction rates in these kinds of things. And so I think it's, I don't feel like I have a good, perfect answer about how those two things are related. They could be related, but they could not be. Yeah, okay. So we formed some melt, and I'll just go back here. So to point out, as in our thermal structure, in our mantle wedge, the temperature is starting to go up now as this mantle rises, as any melt rises. It's encountering higher temperatures as it moves upward. And maybe it doesn't move upward, right? Because why would melts perfectly move upward? There's all these things going on, so they might move sideways. They might not move perfectly upward. But in the general direction that they travel, there's increased higher temperatures. And so you're actually seeing an increase in your melting extent as these rise, because they react with the mantle. And why that is, and the specifics of that, I'm prepared to talk about that in Mantle Melting 101 next week if we want to. So the melts rise, they react with the mantle, so they're not probably in straws or diapirs or channels such that they don't interact at all with the mantle. There might be some cases where they are in channels, but there's probably lots and lots of situations where they're not. So they're continuing to communicate with all of the mantle minerals in that porous network that they're traveling through. And so those melts are continuing to change. Those fluids are continuing to change as they rise and interact with that mantle. And so that's, there's quite a bit of transformation that happens to them from that point of first formation to that point in which that they're exiting the asthenosphere and entering the lithosphere. And then we get into the lithosphere and the crust. And we start to see all sorts of these sort of down temperature processes of crystallization, assimilation of whatever amount of overriding plate crust there is, mixing of various magma bodies as they choose to stall in the crust. And there is a whole huge body of work that works on this in subduction zones, but also just at other types of volcanoes. But you can suffice it to say, there's a lot of chemical alteration that happens to those melts in the mantle, and then there is a whole lot more that happens in the crust. So part of our job then is to try to back out what these processes are at each step in the process. And that takes quite a bit of work. We come up with models that show the different depths of different crystallizations, and when we mix these two things, what happens and what changes in terms of crystallizing. How do things like the amount of oxygen or the oxygen fugacity, how does the water content, how do the volatile contents change as it goes through all of this very complicated filtering in the crust. And so there's a whole body of work that we do to answer those questions. And I think it's also, we talked this morning a little bit about the straw and the tube model. It's not very good for magma chambers. We don't think that there's these big bodies of molten liquid anywhere in the crust anymore. They are probably mostly cooled and crystallized, and there's little pockets maybe of higher concentrations of melt, and that any melt body is formed by sort of accumulated, repeated injections of small amounts of melt into a system. And so I'm showing this cartoon. First of all, there are caldera volcanoes in subduction zones, which are typically things we associate with very silicic and often intraplate volcanoes. But there are lots of calderas in subduction zone settings. And we spend a lot of time thinking about these sort of crystal mushes, where we have mostly crystals with a little bit of liquid, sort of being the large underpinnings of those types of volcanoes. And those are certainly very relevant for thinking about subduction zones, as well as sort of more simplified cases where we have less stalling and processing in the crust. So there's all of these very complicated processes. And then finally, the part that most people are aware of, boom, right? We have eruption. So we have all of these very famous eruptions, and I put up here sort of our USGS compilation of volcanic eruptions at famous Cascades volcanoes through time. And you can see automatically that these volcanoes erupt with very different frequencies. They've had sort of very, as I just mentioned, there's caldera volcanoes, right? Like Crater Lake. There's volcanoes that are sitting slightly sort of back, like Newberry or Medicine Lake, and have a very different morphology than something that sits out front, like Mount St. Helens. And so these have very complicated histories with very different eruptive patterns. They erupt very different kinds of things, although we can make averages out of them. And so there's quite a bit of work to going on what controls that variability along strike within an arc or between different arcs and different types of volcanoes, and how much of those processes are from what happened in the crust, how much are from what happened in the mantle, and how do we integrate all those signals to see what we get out on the top. Questions? Yeah.
Just curious, places like Crater Lake and such. I mean, what was the timing of the latest eruption? I know the scale stops there.
I don't remember off the top of my head. What was the most recent eruption at Crater Lake?
A few thousand years ago, I think, for Wizard Island.
Yeah.
Not that recent.
Yeah, you can see obviously not on this timeline compared to some of the other ones.
7,000.
Yeah. Right. So, and I also want to touch on, the gases, the devolatilization of these magmas is an important part of story, of not only for understanding what's happening, but also for monitoring these volcanoes. And so we can have models. This is a model for Mount Erebus, which is obviously not super relevant to the things we're talking about, but it's a very nice integrated model that shows you how, when you have different depths of degassing, you have changes in the volatile chemistry associated with that. And so we have the chemistry of the volatiles being released during an eruption and also not during an eruption that tell us something about the subsurface process in addition to all of the rock record. And so we'll have some opportunities to work on that a little bit when Tobias gives his tutorial. And that's another important part of the geochemical cycles that we see at ARCS that have big implications for sort of atmospheric evolution and climate. So when I was thinking about this, putting together, I was like, what are some of the themes that I, as a petrologist or a geochemist, think about in ARCS? Well, I think one sort of way that we could sum up everything that I just sort of walked through is just about us trying to understand what are all of the chemical reactions that are happening in a subduction zone during the sort of metamorphosis of the slab, and then with the interaction of this giant geochemical gradient that is set up with the mantle wedge, and then within these smaller geochemical gradients between melts and mantles, and then again very large geochemical gradients that are within the crust. And so our whole questions is trying to figure out what are the components involved in each of these geochemical reactions, what are the coefficients of those reactions, i.e. what are the proportions of each of those components in the reaction, and then what are the rates of these reactions. And that's sort of, I think, one way that you could sum up the kind of work that we do when we think about these systems. Another way you could sum it up is to say we spend a lot of time about trying to think about fluxes. What is the flux in versus the flux out versus the flux down? What makes it into the deeper mantle? What makes it out into the atmosphere or into the surface environment? And what is ultimately recycled or goes in the first place, so that we can calculate large-scale budgets over time, large-scale fluxes over time. And then there's the cycling part about it. How often that things go down, come out the top again. What are we net adding to the mantle over time? What are we net subtracting to the deeper part of the planet over time? So it's sort of this story of reactions and fluxes and cycles. And just really at this point in the game, we're really interested in sort of the forefront, I feel like, is really, wanting to put very quantitative models together to model these processes, as well as to try to figure out the time scales and the rates of these processes. So, of course, when you're doing your job well, you're asking lots of questions. And so I'm going to talk a little bit about tools, and I'm going to go through that a little bit fast, and then we'll have some time to just sort of talk about remaining questions and roadmaps. So maybe implicit in what I said already, what are the tools that we use as petrologists? Well, we spend time in the field. We go to these volcanoes. We collect the rocks. But in addition to collecting the rocks, the samples themselves that we want to study, it's very important to think about their context, their relationship to one another, their structures. And to do that for samples that have been exhumed to the surface and try to reconstruct their paleo environments to understand what's happening where we can't see deep down in the mantle or in the slab, as well as those accessible samples on the surface. We spend a lot of time looking at their chemical compositions, both the compositions of the gases and of the lavas and every component in between, and trying to understand what those can tell us. I mentioned experiments quite a bit. These are a great tool for trying to replicate environments that we can't access and to reproduce processes that might otherwise take millions of years, such that we can form them in a subduction zone. And we used all of these kinds of tools then to create geochemical models that allow us to take something and then, assess its pressures and temperatures of formation, for example, or what were all of the components in that reaction that formed it and their relative proportions. And then lastly and importantly, then to integrate these with observations from other disciplines, or do that concurrent with all of those other methods to try to develop better sort of synthetic or overarching pictures. So I wanted to talk about these just a little bit. So when we have rock sample types, we're actually talking about quite a lot of different sample types. Often as geochemists, we talk about bulk rock samples. So this is, for example, just a hand sample. So if I went to a volcano or I went to a piece of a subducted slab that is now exposed on the surface, and with my rock hammer, I just knocked off a big piece, a bulk sample is what I get, right? And it's an integration of all the different minerals and melts that might be in there, whatever might be in there, but it's an average of the whole. And so we often will take this and we'll crush it up and we'll do geochemical analyses by methods like XRF or ICP-MS or TIMS, which are all different ways of just getting an analysis of that bulk, everything averaged in there together. And those are good for giving us senses of the overall processes of formation of a sample, sort of bulk characterization. What kind of rock is this? What's its general setting? What is the general processes that formed it? We increasingly spend more and more time looking at sort of the components that make up that bulk sample, the minerals and or melts that might be present. So this is looking at the individual crystals or parts of those individual crystals within that bulk sample. And those are really important for sort of now taking that bulk story, like what was the main process that formed it, and then backing out a higher resolution story. What were the steps in the processes of formation, and more information about the conditions of each one that led up to having that bulk sample. And so key to doing this, for example, are things like zoned minerals, where we have many layers of time essentially that we can go back and probe and look at variations to. And so for these, we need in situ geochemical techniques to go and measure a little spot, right there versus right there versus right there versus right there versus right there, to see those changes with time within a particular crystal. And that might be the history of this, integrated history of this crystal, and then I can go to a different one of a different type and do the same thing and understand how that mineral formed relative to this mineral. And so this is sort of an increasingly important part. The sort of ability to have finer and finer analytical resolution has really enabled this. And then also we hear quite a bit about the importance of melt inclusions or fluid inclusions, which are even trapped within these minerals, right? And these are essentially a time capsule back to earlier in the rock's history, when that crystal grew and trapped a little bit of melt. And that melt has long since gone and evolved and done other stuff, but we can go back and see what that is. And again, we have to have very good in situ techniques to measure that, but that gives us a hint back to an earlier point in time of that crystal. So these are some of the main, when we talk about rock samples or analysis types, these are some of the main things that we use. And then we take the information from those analyses and those sample types, and we love to plot them up on all these complicated diagrams that usually make, geophysicists get annoyed with us. And they tell us things about what are the main processes that contribute to the rock formation. So in this case, we might be plotting the bulk sample composition, and it would tell us, oh, this one's a product of wet crystallization, i.e. it came from one of those wet melting scenarios and then crystallized with water present, whereas this one is a dry one. And, or we might look at something like this, where we're plotting up, this might be in situ data, or it might be bulk data. We're looking at the trace elements that have smaller abundances, and we can plot them up and we can say, oh, if they have more barium over thorium, these two elements, that tells us that they were, aqueous fluid was really important in their formation, whereas something down here, sediment, was a more important in that chemical reaction that I'm trying to write. What were all the components that were involved in forming their rock, and what was their relative proportion? This helps us do that. And I'm putting down here, for example, so on Thursday next week, you'll have an entire tutorial that will help sort of decode some of this stuff and hopefully make it a little bit more accessible. Another really important tool in sort of understanding all these systems is looking at the isotopic composition, whether that could be the bulk sample again, or it could be, again, those parts of an individual crystal or a crystal as a whole that we're using. And those are very important to telling us what were the different components that were involved in the formation, especially in the mantle, for these individual samples. And we have all of the wonderful initials of different things in the mantle that might be contributing to forming this. And we'll save that for having Matt help guide us through next week. And then isotopes are also really important for helping us think about age constraints. Most commonly, we use the decay of parent isotopes to daughter isotopes with different half-lives to help us know the absolute age. So this rock, erupted on the surface 100,000 years ago, or this rock experienced a metamorphic event that reset these minerals in it that have with the isotopes, 2 million years ago. And when we do that, so that's putting our rock in absolute time, but also increasingly we're able to use isotopic systems and the disequilibrium between them to get at more information of duration of process. How long, we mentioned earlier, there was a question about maybe we could use uranium series isotopes or radium disequilibria to look at how long it took for something to happen. Like when did that melt separate and form, and how quickly did that happen in a wet setting versus a dry setting. So there's duration of processes, and length of processes is also something we can get at with isotopes. Okay, thank you. We have all these amazing geochemical databases. So now that we have more and more online data, we're able to take these geochemical databases and sort of, have much larger data sets. Instead of it only being the ones we can go out and collect ourselves, we can have access to sort of as many analyses as have ever been done before has been uploaded to a database. With the extent that obviously you have to go through and do quality filtering and all of that kind of stuff. But there's increasingly large data sets available to us. And this is a list of some of them. And I made it so you can click on these and it'll take you to the database when you look at the lecture online. And there's different kinds. This one's all North American volcanic and intrusive rocks. This one's all igneous and metamorphic rocks from the ocean floor and xenoliths. This one I misspelled. This one is this one is one that's supposed to be like every reservoir on Earth. Here's some good example average analyses from it. This one's partition coefficients, how certain elements are divided between different things. So these all exist to us now. They continue to be developed and increasingly more accessible, and they are important tools in doing research. And these are great fodder for research projects when you guys come time to sort of work on something. If you want to get what is the global average composition of this, or how variable is that, these are great tools, and you'll be getting to sort of engage with some of that in a tutorial next week. And there's more and more papers now that essentially are taking a statistical approach to solving these problems. You're using very large data sets from these kinds of, and then doing sort of bootstrapping techniques, for example, to fill in where we might have observational bias or be missing samples, to then solve big problems where having a lot of samples is really helpful in looking at average distributions of things. And this is a growing field. This is happening more and more and more, and you're seeing more and more publications like this. And so how to do it well and how to look at these large data sets is an important question in geochemistry today. I have some slides in here about experiments, but I kind of already explained. My favorite little thing is to say it's like a submarine where we can go down and we can experience all these great processes. But what we're really doing is we're going to one pressure and one temperature in an experiment, and we're saying what minerals and or melt are present there. So it's just like a fill in the dots exercise to a large extent, right? So here's pressure and temperature increasing, and these are different minerals in this key here. So you can see different boxes have different parts of them filled in. And I went through and we did all these experiments, each one at different temperature, different pressure. We see whether or not there is a mineral or melt there, and then we connect the dots and we say, oh, there's a phase boundary here because all of the ones to the right of this line, you know, have plagioclase, and all of the ones to the left of this line don't. So that's the condition at which plagioclase becomes an important player in this example. So that's the nuts and the bolts of doing an experiment, and it's a very important part of building all of the geochemical models that you ever see. And ultimately, somewhere early on in their genesis, there's information derived from experiments, if not most of it. So we take these compilations of experiments, and we take their temperature information and their pressure and their composition, and we're able to write equations then that sort of summarize the data sets and do regressions through them. So we can have both forward models and backward models. We can have models where we take a rock composition and it inverts through these equations to give us the conditions of formation, or we can have forward models where we say, I want to know what rock would be present at these conditions with this bulk composition, and it spits out one for us. So we have both of these kinds of geochemical models. And I'll skip this for now. We have tools for phase equilibria that are really good, for example, for metamorphic rocks, where you might not have silicate melts present. And then we have other tools that are much better at working with systems where you have melt present and all the processes associated with that. And we're going to have time in tutorials and lectures to talk more about these. And then another really important thing that we do is we want to know the conditions at which these rocks form. And so we do that by using different minerals or melts that have a strong temperature dependence or a pressure dependence. So a reaction, for example, that has a a very sharp change is a very good thermometer or a good barometer. And so so example I always use is olivine, your first phase diagram of cider. So temperature increasing here, and this is the relative ratio of magnesium to iron plus magnesium. And so when we're starting up here as a liquid and we're cooling off our liquid and we start forming an olivine, this is the olivine composition. It has more magnesium in it. And this is the liquid composition. And then as we continue to cool and crystallize it, our olivine has lower and lower magnesium in it, and our melt follows this trajectory. So obviously the composition of olivine is a very good thermometer. It changes quite a bit as a function of temperature. And so there's lots of mineral phases that are good for these kinds of things, or other ones that are good at pressure dependences like this that make them good for doing those. There's nice review papers on these kinds of systems. There's different kinds of things that are pressure or temperature dependent. It might be the exchange of, for example, iron and magnesium between two different minerals. It might be that example like olivine I just showed you where the composition of itself changes, or it might be the balance of composition between a melt and a mineral that change a lot. And those are all different things that make good thermometers and barometers, and we'll have more time to talk about that. And so we can do all these cool things with them. We can say, oh, I want to know this primitive basalt that erupted. I want to know what pressure and temperature it formed at in the mantle. That's an example I'm showing here, and it's plotted on top of a seismic model, an ambient noise tomography model under the Cascades. I can use this nice image here from Adam that shows we can take all these different kinds of pressure constraints for all of these different magmas that erupted at Mount Hood and say, here's, if I use this model or this model or this model or this model, or this one's volcanic earthquakes, here's all the different pressure ranges that I get from how it formed. Or I can use these thermobarometers to say what was the pressure temperature history of my metamorphic rock in time. What was the trajectory that it took? So these are all really important tools for us. So I have a whole bunch of things that I wrote, and they're like I teach a science communication class, and this is exactly what you're not supposed to do, which is just put lots and lots of text up here. And I'm thinking of this more as a living document, so that when I upload it to the wiki, you guys can all go download it, and you can look at it, and you can think about it, and you can ask questions. I am not going to read this. But the point is that there's like a whole host, a family of questions about the slab, you know, that I touched on when we were walking through all of these things about things that we don't know of about the slab, about the mantle wedge, about the lithosphere and the crust. And these are all kind of questions that might be prompts for research projects. They might be themes that we want to discuss as a whole, as a group more, and all of that kind of stuff. So I'm going to finish up by just walking you through those contributions that I mentioned in the context of my cross-section. So we have, starting tomorrow, Sarah's going to lead us through a lecture sort of talking about the constraints that we have from the subducting slab. We also have a tutorial tomorrow where we're going to have access to a whole range of rocks from subduction zones. And we're going to be able to kind of like put a physical rock with these maybe images or associations or cartoons that you have. And this, on Saturday, we're going to get to go to a field trip. We're actually going to get to put your hands on some sort of melange and slab material. So we're going to start off with sort of all of this information. Then we're going to kind of skip the mantle wedge for now, and we're going to move into the arc. So what's exposed on the surface? Adam's going to lead us through a lecture thinking about how we construct the volcanic arc. And then we're going to have a tutorial next week where we talk more about some of those tools that we use to understand all of those processes that happen in the crust and building of the arc. And then on Friday this week, Paul is going to lead us through sort of a discussion of the role of fluids in subduction zones. So that's sort of a more integrated over the whole subduction zone itself. Tobias is going to work with us on Friday in a tutorial about the gas geochemistry coming out of volcanoes. And so we'll get to sort of explore the relationship of that to the arc and other things. And then next week, in our week 2, we have a whole host of things where we're going to think about rheology, we're going to think about deformation, which I included here sort of in the broad sort of geology category. And then I'll talk more about how we melt the mantle, and Matt will talk more about isotope constraints in the context of a subduction zone. And then finally, at the very end of all of our lectures, Terry Plank is going to give us a very nice sort of summary and what's the future look like with the subduction zone initiatives that are being proposed to sort of have the next era of subduction zone research after GeoPrisms and EarthScope. And I also just want to highlight that we're going to have all these amazing senior participants who are going to be around this whole time to engage with you. And these are all individuals who fall under the sort of geology, geochemistry, petrology family. And so there's going to be many, many resources for you to engage with us in the next couple weeks. And I'm really looking forward to it. All right.
Okay, I think we have time for a few questions, and I'd like to see some questions from students also.
Yeah.
So at the beginning here, let's take only questions from students or postdocs. We might have to wait a while.
That's all right.
Yes,
that's
back
all right.
there.
So in your presentation, I missed one cartoon. I did not see when the ocean is subducting. What is the other side? The continent lithosphere is missing always.
Yeah.
So what's the role of the on the forearc when there is a thick lithosphere?
So you're saying sort of east, like or on this in this cartoon to the east of the arc. Is that the question? Yes. Sort of what's happening there? Yeah. Well, so arcs are complicated, right? They're not like a perfect single linear feature like we show them in cartoons, right? So there's all of that. There's also in some cases there's very developed back arc volcanism, and in some cases there's not. And so, it's really dependent, right? There's so many structures. There's places where, in South America where we have flat slab subduction, or maybe earlier in North American history with flat slab subduction, where that sort of structural role propagates very far inboard. And then there's other settings where we have really steeply dipping slabs where everything's really close to the trench. So I'm not sure how to answer your question, because it seems like there's many, many answers to your question. But certainly in continental arcs, where we have a continental overriding plate, which is sort of the cartoon that I was using, the role of pre-existing structures and thickness of continental lithosphere are important considerations, which might be less important in an oceanic arc. Yeah, that's a very general answer to your question. I'm sorry.
More questions by students and postdocs?
I apologize if I missed you saying this, but in your experiments, do you have to take account of metastability in the various phases? And if so, what do you do?
Right. Well, so you're getting into the topic of equilibrium, right? So the question is, can we assume, or is it a valid assumption to make when we look at these systems, that everything's in chemical equilibrium with each other, right? That they've reached some sort of steady state. There's probably some cases where the answer is yes, and some cases where the answer is no, right? In cases where we expect there to be chemical equilibrium, right? Well, in experiments, we obviously want to get to that chemical equilibrium. So we can do all sorts of things to try to assure that we've reached it. We can do time series, where we run experiments for different lengths of time and make sure we still get the same answer. We can do reversal experiments, where we put in essentially one set of things and see if we cross a reaction boundary, and then we can try to cross the reaction boundary from the other direction, and make sure that we get the same thing. We can sort of do things like that to say, yes, this experiment was at equilibrium, or no, it wasn't. There's lots of places where disequilibrium is maybe not a good assumption, right? In some cases, the reactions between fluids or melts with the solid materials around might not be in chemical equilibrium with each other, right? And we can certainly do experiments where we're not at chemical equilibrium. The question is trying to figure out rates of those reactions, and so we can sort of assess where we are on the equilibrium to not equilibrium spectrum. There's also lots of places where actually in trying to understand time, disequilibrium in isotopes and disequilibrium between different parts of a mineral act in our favor to help. We know that it's that the duration of that process has been short enough that you haven't reached chemical equilibrium. So we actually exploit that quite a bit and look for that. There's experiments that we do where we're trying to take two things that are out of equilibrium and sort of halt them in the process of coming to equilibrium to figure out, diffusion rates and things like that. I don't know, did that answer your question? Okay.
More student postdoc questions.
Or one over here, Doug.
Here.
When you were talking about the interconnectedness of melt in a crystal structure and how only a small bit of melting can actually be interconnected, what data is that based on?
Well, that's not my particular expertise. So there's experiments that are done to try to figure out how, depending on strain rate and pressure and temperature and grain size and things like that, how that happens. And there's sort of, we need like Uli here or somebody. We also have other ways of sort of imaging, like say you could take the tomography of a very small sample if you have something, right? And you can try to map it in 3 dimensions and see the network structure, the permeability or something like that of a sample that exists. What else am I forgetting? Models.
I sometimes see experiments with electroconductivity.
Right, exactly. Right, that's an important part of doing it.
But so those experiments that you're referring to, they're on a small-ish sample where it's all relatively at the same temperature pressure condition.
Yes.
So when you're thinking about a subduction zone where it's, you know, the like a large region's not all necessarily at the same temperature, then that how does that kind of translate into how we think about the way melt is connected in a larger setting?
Yeah. Well, I would say that one of them, like in my mind, one of the most pressing and long-standing unresolved questions is how melts and fluids move through the mantle in a subduction zone. That's something where we're starting to make some progress, but we have lots and lots of unanswered questions. It's an important forefront of what we're doing. A great thing for this group to talk about.
Other student postdoc questions? Yeah, over there.
Yeah, I guess connecting that question with what we were talking about this earlier today with geophysics. Like in your cartoon model, we've got like this long interconnected thing of melt.
Yeah.
Like, is that imaged geophysically?
No. That is very cartoony. I mean, what I think we have some constraints, say, for example, that there must be, based on the chemistry, based on the petrology, that we have to have what we call reactive porous flow, where those melts are reacting as they go, because they continue to record changes in the conditions along their path. And so there have to be, to some extent, interconnected networks that facilitate that. But there's probably also, we also have chemical evidence from the magmas themselves that they are sometimes in channels. And especially, I think it's an important question to ask in the lithosphere, how much we're having the reaction with the ambient lithosphere and how much we're sort of more having channelized flow. And so not only do we think that both exist, or probably a continuum between those two things exists that are, there's lots of fluid flow models those are sort of the two end members, but there's lots of things in between. Not only do we probably have a spectrum of things there, but trying to image that, right, when we don't even really know what we're looking for exactly, or it's on such a small scale, and can we resolve that? It's not a unique solution. There could be this % of melt with this interconnected network, or there could be this % of melt with this not interconnected network, right? It's really hard to look for those things. So those are really, wouldn't it be, I think there are lots of people who in this room would be ecstatic if we could image that. But I think we're still on our way, and people here who work on that, feel free to chime in with more. Well, you want to talk about it now?
I mean, I think overall there's been kind of this evolution from seeing sort of magma being concentrated in sort of big volumes,
right,
like big chambers, to, mostly flowing through porous flow and channels, and actually even when it does collect, it's probably not in some huge, gigantic chamber, but in a pressurized system of conduits.
Right.
So
I think that's been an evolution of our thought, say, over maybe like the last 10 years. We really evolved, and that's from studying a large part natural samples, that we've come to understand that that's not a good model for what we're looking for. But in terms of actually being able to image that, it's another ball of wax.
Was there another question over there? Yeah.
Okay, part of my research is actually looking at magma addition rates to the upper crust, to the arc crustal column of different arcs worldwide. And there's quite a difference, actually. And I was wondering, so for me, that reflects processes in the mantle below.
Yeah.
And I was wondering if you could comment on what your thoughts are and what could cause that.
So cause the difference in
magma addition to the upper crust. So I see arcs which have very high magma addition rates on like an arc kilometer, and others which are very low. And
so how are you estimating addition? Are you saying?
I basically look at maps and make some, I mean, they're based on assumption. I make some assumption of what I think, how much magma was added over a certain amount of time and certain amount of area.
Okay.
And then
so things that are erupted on the surface.
Yeah, so I look at different crust levels and see how that changes, but I also compare different arcs worldwide and just think about throughout the same amount of time you have changes in magma addition to the upper crust.
Right.
And
I mean, like a lot of my answers to these questions are like, that's a really important problem and I have no clue. So that's a good thing for a CITER to work on, right? So like, yes, all I can say is that it arcs. It's exciting to hear, I look forward to seeing your poster, and seeing how those things, putting quantities on those, they compare. Because we do know quite a bit that there's a lot of variation in both, like I showed, like the frequency of the eruptions, the types of the eruptions, the amount of volcanic material versus the type of plutonic material, the spacing of volcanoes. Like there's a lot of variation in arcs, right? And so I think a lot of the work to date, because of the necessity of science and tractable problems, have tended to focus on individual volcanoes or individual arc segments in terms of kind of trying to build up our understanding. I walked through all of these processes, and those are based on years and years and years of research, right? When I look forward, I think some of the really exciting questions we can ask are now trying to take those and build like more cohesive quantitative models. How much of the signal that we see at arc volcanoes is controlled by the crust versus the mantle processes? Now that we start to have a sense of what they are, how relatively important are they? Is what's coming out of the mantle fairly ubiquitous at arcs, and it's the crustal processing that really varies, or is it that there's so much variability in the mantle that really sets up the variability? That crustal addition, you're talking about the magmatic addition, right? That is a productivity question as well as a structural question, right? Some arcs that are really compressional, less things are going to make it to the surface than arcs that are really extensional. What makes it to the surface will depend on how much time it's stalled in the crust. And so what controls how long magma stalls in the crust? There's like all these really cool questions there. So I look forward to talking about them with you.
Thank you.
So the very first thing that's important for a subduction zone is the formation of the subducting plate itself, right? So that actually starts over here at the mid-ocean ridge. And as Peter discussed this morning, there's all sorts of important processes that sort of set up what's going to happen in the subduction zone in the mid-ocean ridge environment. There's melting that's happening here to source the magmas that then go on and form the oceanic crust part. There's a slow cooling that facilitates the formation of the mantle lithosphere part of that oceanic lithosphere. There's, I don't have it written up here, but there's the deposition of sediments away from the the ridge axis. And there's hydrothermal circulation, which is a really important mechanism to introduce fluids close to the mid-ocean ridge. But then there's also very important outer rise faulting that we talked about this morning that introduces fluids not only into the oceanic crust, but into the oceanic lithosphere portion of the slab. And so it is this setup that is so elementary to understanding the flux into a subduction zone environment. You really can't understand what, the sort of net cycles without understanding what's going in.
Christy?
Yeah.
Do we have a sense of the relative importance of the hydrothermal circulation versus the bending fractures in terms of the water that they produce? Are they comparable or are they different?
That's a great question. I don't know, Magali or anybody else want to chime in? I think, yeah.
Are you talking about hydrothermal circulation near the mid-ocean ridge?
But it ultimately adds water to the flux.
That's an important.
You can have hydrothermal circulation in the cold bending area too.
Right. So there's hydrothermal circulation close to the ridge axis, which has certain chemistry associated with it, certain temperatures associated with it, and then there's additional hydrothermal circulation as you sort of move to cooler parts. There's also the outer rise faulting. I remember having a conversation like early on, maybe in my master's degree, where someone was like, that was not discussed at the time as an important mechanism. And so, the evolution of that as an important mechanism or maybe a main mechanism to introduce water into the subducting slab has really, at least in my knowledge, has really grown in appreciation since, the late 2000s. And so, to be able to say the ratio of how much one versus the other introduced, I think is an open question, at least to my knowledge. one thing that's clear though is that because of the amount of oceanic lithosphere close to the axis, the amount of water that ends up in the oceanic lithosphere is a really important component, and probably those outer rise faults are a very important part of introducing it into that colder, more developed lithosphere, depending on where the axis of the ridge is relative to the trench, obviously, but yeah.
So in my naive mind, hydrothermal circulation means hot stuff is going up, and the outer rise faulting means cold stuff is going down. Is that something that you could distinguish geochemically?
I'm sure there's ways we could think about how to distinguish it, but I guess we'll go ahead and get going with our afternoon program. How's everybody doing? How many jet-lagged people do we have who are starting to die? A couple. Yeah. So I'll try to keep it lively to keep you awake. A couple people have asked me, the printed out paper schedule that you got in your folder yesterday or this morning, there's some errors in it. And it includes things like the 2 Fridays for the lectures are identical. So that's not happening. We're not doing the same thing repeated all over again. So when in doubt, if you guys go to the CITER webpage and look at the agenda on the wiki, that is correct. So the default for you should be the wiki and not the printout. But if you have questions about the schedule or when there'll be time to do certain things, you should definitely feel free to ask myself or Peter or Doug. And well, there's some flexibility built into the schedule, not a ton, but there's some. So we can handle. I have a couple people ask me things already about can we fit them in. So. Any other sort of like logistics or questions before I start talking about petrology and geochemistry? Yeah, are you raising? You're not raising your hand.
I was stretching.
Okay, we can all do like a group stretch together before we start. All right, so I'm Christy Till, and I am one of the organizers, and I'm going to give a very broad view of what we think about as a petrologist or a geochemist, or even just as a geologist who's looking at a subduction zone. So how we look at those things and what that view might look like if you could put on your petrology glasses and see the world through them. What would you be seeing? And to start us off, this is a line drawing that I did as the advertisement for my PhD defense a number of years ago. And I think it actually kind of encapsulates some of those things. I was thinking a lot about subduction zones and how mags were generated in subduction zones. And you can see like the scale of certain things is like very disproportionate to reality, which reflected the things that I was thinking about a lot, right? Those birds, for example, are definitely not to scale compared to the mantle wedge, but yeah. So I'm gonna go really broad here. I really want you guys to interrupt me constantly, ask me tons of questions. I'm going very, very basic. So if you have a question about something that's, trying to go more advanced, that's great. Or if you have something that's like really basic, like this week, and especially these first couple of days, these are the times to like ask that really, really simple question. And there's no shame, okay? So please interrupt me. And we have the microphones, but another strategy is to just really shout, so. Okay. So I thought I'd just say a few words about who I am, since many of the students, for example, probably have no idea who I am. I am a petrologist, and mostly I'm an igneous petrologist, although I look at metamorphic rocks, or sometimes you can ask the question, what is the mantle? And I look at the mantle, so if it's igneous or metamorphic. The main instruments that I use are experimental apparatus, which you can see here in our lab at Arizona State University. And so these are a range of piston cylinder devices that cover from 0 to 4 GPa and up to about 2,000 degrees Celsius. So we're looking at the lower crust and uppermost mantle part of planets. Here's my wonderful research group. And we have, a very broad interest in how magmas form. I would say the sort of biggest question or the broadest question we ask is sort of how do magmas form in the context of planetary bodies? Over what timescales do they form? And what role do they play in sort of the formation and evolution of planets? But some more specific questions is we think quite a bit about how the recycling of oceanic plates produces volcanic arcs, so the magmatic sort of cycle of a subduction zone. We think about what are the specific events in a magmatic system leading up to an eruption and trying to back out the life story of a magma body before it erupts, and specifically the time scales associated with each of those events prior to eruption. I'm working on exoplanet mantles, trying to understand melting behavior and crust on exoplanets, and also thinking a lot about how subduction zones and the roles of the solid Earth might have contributed to the rise of oxygen in the Earth's atmosphere, what we call the Great Oxygenation Event about 2.3 billion years ago. So a very broad range of interests in magmas. So please, I'd love to talk to each and every one of you about anything of our interest that might overlap during the next several weeks. So I look forward to having conversations about all of those things and many more. So I'm going to talk about a couple of things here you can see in the outline. I'm going to first just really basically walk us through the key components and processes in a subduction zone if I'm wearing those petrology colored glasses or a geochemistry colored glasses. What are the things that pop out to me? What do I look at? I'm going to talk about some of the key tools that we use as geochemists and petrologists, and then sort of think a little bit about what are the big picture questions that these communities are thinking about today. And I'll end with sort of a roadmap for all of the geochemical and petrologic and geological contributions to the lectures over the next couple weeks and show you what the roadmap is for those and how they're going to fit into this big picture that I've just laid out for you. So let's just get started. So here's another cartoon that I'll be using throughout, and we look at a subduction zone in a cross section mostly, right? We're not quite advanced enough to look at it in 3D on most days, and then the reality is we think about it in a cross section, but that is a very idealized cross section. As we were talking about this morning, the slab is not like a perfectly linear feature with like sharp boundaries or anything like that. But we think about it like that because that's the models that we've developed. And so we always have to ask ourselves how much of what we're thinking about or interpreting is based on these models we've created for ourselves, or these cartoons really, or how much of it is
Circulation starts off as cold stuff going down.
Right, exactly. I was going to say that the characterization of the stuff near the axis is actually starts out cold, right, and then it gets heated up. So it's a little bit more complicated than thinking of them as being sort of two separate thermal regimes. Yeah. Do we have, Samir has one and then Magali has the other. Okay, so we can have maybe volunteer runners who can like run around. If you want, like if you're afraid you might fall asleep after lunch, that would be a good activity for you. Yeah, all right. So this is the setup, right? And then I just thought I'd touch briefly on, well, what are the materials themselves, right? So that slab that we've created, essentially, we can think of it as three basic parts. The sedimentary layer that caps the top. And this is often examined by looking at drill cores of various types. And there's both biogenic and terrigenous or continental derived sediments that contribute to the sediments that sit. So they're not uniform in composition, they're quite variable in composition. They vary in terms of where they are globally, in terms of the amount of those two components. They vary in their thickness depending on how old the oceanic crust is, and so they are a variable and important component. We have the oceanic crust part, and in the simplest sense, This might be the part we're most familiar with. We think of it as a basalt, a mid-ocean ridge basalt, with a fairly uniform composition, although that's not in fact true. There is variation in the composition. And then the maybe most dominant portion of that subducting slab in most cases is that lithospheric mantle. So that is volumetrically quite significant, and it in fact, is an incredibly important reservoir for water and other elements that are volatile, that are carried in volatiles. And the mantle itself is broadly, we call it peridotite. That means that it's made up of olivine, which is this nice sort of candy apple green here. Pyroxene, which in this one is a darker green, that's kind of hard to see. And then variable amounts of minerals that have aluminum in them. So in some cases that's feldspar, in other cases that's spinel, in some cases that's garnet when you're a little bit deeper. And that the ratios of the aluminous phase vary, and therefore the relative proportions of olivine and pyroxene can be more or less dominant compared to these. When we start talking about melting the mantle, these aluminum-rich phases are the things that melt out first, and these are the more residual things, the things that are less likely to melt. And then when we start adding that water to the oceanic crust and lithosphere, we are then developing additional minerals in the subducting plate that are hydrous in nature. And the ones that you hear most commonly discussed and are the dominant ones for these compositions are amphibole, which has about 2 weight% water, serpentine, which we've heard a lot about already today, that has 12 weight% water, and my personal favorite, chlorite, which is, is there a different way that I could be thinking about this? But this is how, in my head, when someone talks about a subduction zone, that's the context I'm usually putting it in. And the reality is that most people who walk around the surface have never seen this or heard about this or think about this. They think about this, right? And maybe they don't even include this part, right? They might be vaguely aware that there's a chain of volcanoes up and down the Pacific Northwest if they're in America, or in the Ring of Fire, and that those are there, and that they're maybe aligned in some distribution. And it's also important to think about that these are, when a geochemist is interested in thinking about the processes that happen in a subduction zone, these are the main places that we go, right? So any view that we have of a subduction zone is biased to what these tell us. Because that's where we've been able to gather the most information so far. It's not that there's other sources of information, it's not that we don't look at them, but just historically, that's where the majority of our emphasis has been so far, and so our view is biased towards those. So we kind of divide the subduction zone up into sort of quadrants or parts. And we tend to, even within the communities of petrology and geochemistry, we don't all work on the same parts, right? So one part that people tend to divide out is sort of the subducting slab itself, and the materials that are in it and the processes associated with the subducted slab. There's the mantle wedge. Here I'm including the lithosphere part of the mantle wedge, but sometimes that's not. The asthenosphere part of the wedge, and that's like a community of people, community of tools who focus on that. There's the crustal part, in which I'm including the arc in that, and there's a community who focuses on that. And it's not that any group of scientists don't cross those boundaries, but we do sort of self-organize in some broad regard into those. And so not only do we need to be interdisciplinary in our geophysicists talking to geochemists, but it's always really good to make sure that the views that we're thinking about in the arc are linked to what's happening deeper below. Like a lot of cartoons, right? They go like, a cartoon of a volcano ends in the upper crust, right? They don't go deeper than that, right? And so how do we sort of think about these as a whole system? So, and then there's volatiles and magmas which transit through all of these different parts. And so they are the parts that sort of link all of these and force that sort of cross pollination of discussion as they migrate through the whole system. But as geochemists, these are sort of maybe the ways that we most commonly, or at least I can't speak for all geochemists and petrologists, so this is certainly biased towards my view, but that I tend to sort of divide things in my head or see the world of science divided into. So what I'd like to do now, I'm just going to sort of step through a subduction zone and say, as a geochemist or petrologist, at each step along the way, what are the key things that we're thinking about? What are the key processes? So this is going to be really basic, but hopefully useful and sort of just going back to the knowledge so that we can all be on sort of the same playing field as we talk about this stuff. So